in this screencast, we are going to talk about the SN1 reaction mechanism, as well as different reaction conditions that apply to the SN1 reaction. So if we were to draw the mechanism of the SN1 reaction, we have our alkyl halide here, and generally, right, how it's shown is it would be shown like this. Right? And this would be a generic predict the product, show the mechanism and predict the product question. Okay? And so what you have to do is you have to say, okay, this is an SN1. And so you come down here and you redraw the alkyl halide because it's a two-step mechanism and you want to show the first step. And the first step is heterolysis. So this bromine is going to break off. Right? So it undergoes heterolysis. And it forms a carbocation where the bromine left. So now we have a carbon that has a positive charge. What happens now, and I forgot a negative charge, so don't be me, go back and fix that. What happens now is we have this negative charged nucleophile, so that's how we recognize our nucleophile. It has that negative charge. And it's going to come in here and it's going to attack that positively charged carbon. Negatives and positives like each other. That's why we see that attack. That arrow shows we've now made a new bond. So when we come over here to write our products, I always start and I draw what's there. And then I say, okay, hey, look. I'm going to come down here because that's where my arrow was. There's my oxygen. And everything that was attached to the oxygen is right there. Now, if you don't like the way that's drawn, I want you to understand that you could draw it like that as well. Both of those are the same, okay? So draw it however you feel. So the second step was a nucleophilic attack, okay? Now, the key feature here is that it has two steps and that you have a carbocation intermediate. Now, in the previous screencast, we talked about kinetics, and I just want to review those. So this is an SN1 mechanism. It's under first order kinetics because it's unimolecular. So the rate only depends on the concentration of the alkyl halide, which if we were to do this specifically for this reaction, it would be CH3, 3 carbon Br. Okay? And so the big take-home message here is the nucleophile doesn't appear in the rate equation. So the rate is solely dependent on the identity of the alkyl halide, and we're going to talk about that as we go through this screencast. Now, it is helpful to look at the energy diagram for an SN1 reaction because this helps us visualize the two steps. We see here, right, the loss of the bromine through heterolysis and that partial positive charge being formed, and then here is our intermediate. Then the intermediate goes through and reacts through another transition state again to give us our products here. So we have two steps, two energy barriers, and the first step here is the rate determining step. Now, stereochemistry also gives us a window into this reaction mechanism. So to understand the stereochemistry of an SN1 reaction, we need to look at the geometry of the carbocation intermediate shown here, okay? In the carbocation intermediate shown here, we have a vacant p orbital, okay? So the carbocation is sp2 hybridized and trigonal planar. it contains an empty p orbital. And that p orbital extends above and below the plane here. And so the three groups here, when we say they're trigonal planar, they have 120-degree bond angle shown here, and that's the sp2 hybridized. Now, what happens is the loss of a leaving group generates this carbocation, and that's planar. So it's going to sit on a flat plane. When we say something's planar, it's like if you can view a piece of paper, all three of these bonds are on a piece of paper, and this is above the paper and this is below the paper. Okay, so it's planar, it's going to sit flat. And so now this guy is just really planar, it's sitting flat. And what happens is that the nucleophile can come in and attack from above or below the plane. Now, your book is going to say in front of the plane, and that's like above, or it can come in and attack below the plane or from the back. And so when it comes in and attacks above and below the plane, even if you start with something that's enantiomerically pure, 1 enantiomer, what happens is you get a racemic mixture here. So 2 enantiomers form, okay? And that process where you start with 1 enantiomer and you form this racemic mixture is called racemization, right? So let's look at some specific, this was a generic example. Let's look at some specific examples. So here are 2 specific examples of racemization in an SN1 reaction. What we see here, right, is that both of these are reacting with the weak nucleophile water, and we get racemic mixtures in both of these. I want to point out that I like these again because they show you that you get a racemic mixture when your alkyl halide or your leaving group is on a dash or a wedge, as well as when your leaving group is sitting within the plane of the paper, right? So then you can look and see, okay, how does this racemic mixture work? How do I represent it over here in the products? So again, a really great example. Now, the rate of an SN1 reaction is affected by substrates, the alkyl halide. So let's talk about those for just a moment. So we're going to focus in on the alkyl halide, right? And what we see here is that as the number of R groups on the carbon with a leaving group increases, the rate of an SN1 reaction increases. This is exactly opposite of the trend in SN2 reactions. Okay, so we see here that methyls are the slowest and tertiary alkyl halides react the fastest. So that is a really good way. Looking at your alkyl halide is a really good way to distinguish between SN1 and SN2 reactions. And we are going to do that more in the next screencast, but I want to go ahead and point it out here. Now, we are going to spend quite a bit of time for the rest of this screencast digging into why we see this trend and why it's the opposite of the SN2. Now, before we do that, though, I want to give you a summary of everything we've learned so far about the SN1 mechanism. So when we come over here, we look at the SN1 mechanism. It's got first order kinetics. So an SN2 had second order kinetics, and this mechanism is 2 steps instead of 1 step. We end up with a carbocation intermediate, and we end up with racemization if you have a single stereogenic center. Then the more substituted halides react the fastest. So you can see how an SN1 mechanism and an SN2 mechanism differ by comparing these 2 summaries. Now, I'm sure the burning question of your heart is why does the identity of R, right, affect the rate of SN1 differently than SN2? And so let's look at that carbocation stability for just a moment. So what we see here is that we have increasing carbocation stability as we go from methyl to primary to secondary to tertiary carbocations. Now, remember, just as a brief review, primary is determined by the number of R groups, and R groups are just carbon groups. So we see here, right, that there's primary with 1 R group, secondary with 2 R groups, tertiary with 3 R groups. And the reason that we see this is due to inductive effects, and so as well as hyperconjugation. So inductive effects occur by the pull of electron density through sigma bonds caused by an electronegativity difference between atoms. And so alkyl groups here are electron donors. So let's put some words to that. Inductive effects occur by the pull of electron density through sigma bonds caused by electronegativity differences in atoms, right? So alkyl groups are electron donors. A lot of times we can predict reactivity based on carbocation stability and steric hindrance. I would say we use those 90% of the time in Intro to Organic courses to explain the differences that we see in reactivity. So this is critically important. So you might want to star this page in your notes, but it's incredibly important. So what happens is these R groups come along and there's an electronegativity difference here, because all of a sudden we've got this positive charge, and so they donate electron density, and the more R groups you have that donate electron density, the more they stabilize the carbocation. So in general, the more alkyl groups attach to a carbon with a positive charge, the more stable it'll be, right? So now the order of carbocation stability here is also a consequence of hyperconjugation. When we talk about hyperconjugation, that is just the spreading out of a charge by an overlap of an empty p orbital with an adjacent sigma bond. So let's put some words to that. This is just the spreading out of charge by the overlap of an empty p orbital with an adjacent sigma bond. Now, that overlap delocalizes the positive charge. So that kind of like spreads out that positive charge on the carbocation, and it gives it a larger volume, stabilizing that. So there's a larger volume for that positive charge, and it stabilizes it. So let's look at an example here. So in this example, we've got CH3 with a carbocation here. So it's a methyl carbocation. And then over here, we have a secondary carbocation. So what you're going to see here, right, is there's that empty p orbital, and it's there all by itself. Well, here we've got that empty p orbital, and now over here with this CH3, there can be an overlap here, and it kind of spreads out that positive charge. It's kind of like you phone a friend, right? And so he's got a friend that can help him out with that positive charge. So those are the two reasons that we see that tertiary carbocations are more stable than primary carbocations: hyperconjugation and inductive effects. Now, let's talk more about the rate of the SN1 reaction. The rate of the SN1 reaction increases as the number of R groups increase. Okay, so what this means is, right, we increase the rate as the carbocation stability increases. So if you have an alkyl halide that is tertiary, it's going to react faster than one that is primary. The reason this occurs is because the rate determining step is this heterolysis step, where you're left with that partial charge on a carbon here, and the ability of this reaction to go, per se, is all about the stability of the carbocation here. So this reaction is faster with a more stable carbocation. Now, I want to remind you, the rate of the reaction depends on the magnitude of the activation energy, and the stability depends on the Gibbs free energy. Now, there is a Hammond postulate in organic chemistry that relates rate to stability. And so basically this provides a quantitative estimate of the energy of the transition state. So when we talk about the Hammond postulate, all it does is it states that the transition state of a reaction resembles the structure of the species, whether it be the reactant or the product to which it is closer in energy. Okay, so let's look at this with endo and exothermic reactions. So when we look at an endothermic reaction, we have reactants here and products, and the products are at a higher energy than the reactants, and we have a transition state. Now, what we find is that the products are more likely to resemble the transition state. In an exothermic reaction, on the other hand, the reactants are more likely to resemble the transition state. So what happens to the reaction rate when the energy of the product is lowered? Well, right, in an endothermic reaction, which is what we're looking at right here, the transition state resembles the product more than the reactants. So anything that stabilizes the product stabilizes the transition state too. Right? And so when that happens, that lowers the energy of the transition state. Right? And it decreases the E sub A. And when we decrease the E sub A, we increase the reaction rate. Now, if there are two possible products of different stability in an endothermic reaction, the transition state leading to the more stable product is lower in energy, so that reaction occurs more quickly, right? So, the more stable product forms faster, right? Now, let's talk about exothermic reactions. So we have our exothermic reaction here. In the case of an exothermic reaction, the transition state resembles the reactants more than it does the products. And so that means that if you lower the energy of the products here, it really doesn't have an effect on the energy of the transition state. It's similar for both of those pathways. So since E sub A is unaffected, that reaction rate is ineffective, right? So decreasing the energy of the product often has little effect on the energy of the transition state. So the conclusion here is that in an exothermic reaction, the more stable product may or may not form faster since the E sub A is similar for both products. So the more stable product may or may not form faster since the E sub A is so similar, and I misspelled similar, so let's pretend like I spelled it right. There we go, for both products. So then, how does the Hammond postulate apply to an SN1 reaction? Well, for an SN1 reaction, right, the rate determining step is the formation of this carbocation, right? And this is an endothermic process. So the rate determining step is the formation of the carbocation, and that's an endothermic process. So, according to the Hammond postulate, the stability of the carbocation determines its rate of formation. Right? So the more stable the carbocation, the faster it's formed, right? So when we look at this will form a tertiary carbocation. It's more stable than a secondary carbocation, and so that becomes a faster reaction. So let's look at this energy diagram here. What we're looking at here is the formation of two carbocations. We have a tertiary carbocation here and a secondary carbocation here. And what we find is that tertiary carbocation has a more stable transition state, and so it forms faster than the less stable carbocation, that secondary carbocation, because there's a less stable transition state there. And so that's going to form slower. So in the next screencast, we are going to talk about how to predict the mechanism of nucleophilic substitution reactions, which is basically how to figure out, hey, is this going to be an SN1 reaction or an SN2 reaction. If you have any questions, please feel free to stop by my office.